In this video, let's understand the first topic from Unit 3, that is Intermediate Code Generation. Intermediate Code Generator receives input from its previous phase in the form of syntax tree, and that syntax tree can be converted into a linear representation, for example, postfix notation. Intermediate code tends to be machine independent code. Different intermediate representations of source program are: the first one is syntax tree, then we have postfix notation, then directed acyclic graph, and finally three address code statements. Let's begin with the first one, that is syntax tree and DAG. Given any expression, say for example a is equal to b into minus c plus b into minus c. If I want to represent a syntax tree from this, okay, now in this case I don't have a grammar, so I'll represent this tree directly. So according to the evaluation order, that is the precedence of operators, I'll perform this multiplication again over here, multiplication. So I represent this b into minus c as b multiplication, and since this is unary minus operator, I'll just mention it as u minus c as operand. Then again for this expression I'll draw b into u minus c, and we have this plus operator over here. So I combine these two by means of plus. Okay, so we have considered this expression, and then we have a is equal to this complete expression. So the value of this complete expression is at this point. Okay, so I'll just put equal to operator here, a this side, and this will point to this plus symbol. Okay, so this representation is a syntax tree. Now, what is DAG? Okay, directed acyclic graph. Okay, in case of DAG, we try to identify repeated operations. Okay, now so in this case, if you consider B and C, the value which is substituted in this expression for this B and this B will be same. This C and this C will remain same. So if I consider value of B as 3, if I consider value of C as 2, if I evaluate this B into minus C, I will get 3 into minus 2, that is minus 6. If I substitute B into minus C, that is 3 into 2, I'll get the same value. So in case of DAG, you try to find out repeated operations. Okay, you try to find out repeated operations and try to convert this tree into more optimized form. Okay, how do we do that? Since this b minus c is same operation which is present twice, and the value of b and c remains unchanged, I can transform this syntax tree as a is equal to this plus symbol. Since b into minus c is performed twice, u minus, this is c, b into c, so I'll have one outgoing link from here, b into c plus again I'll have one link over here. So this computation, that is b into minus c, is performed just once. Okay, so in this case, if there are any redundant evaluations, meaning repeated expressions, what we do is we represent that expression just once, and this link are taken twice because this expression is present twice. So b into c plus b into c, so this link again. Okay, so this plus indicates that this b minus c is b into minus c is performed twice. Fine. Okay, so that is the difference between syntax tree and DAG. Okay, next there is one more representation, intermediate representation, called as postfix notation. Let me take the same example, that is previous tree which I drew for a is equal to b into minus c and so on. So I'll draw that tree again. A is equal to plus here b, this is u minus c, and again into b u minus c. Okay, so right now I have this tree with me, that is the syntax tree. What is the meaning of postfix notation? It's a linearized representation of syntax tree. What we do is we traverse this syntax tree from top to down, left to right, and note down whatever values are encountered on the way. Okay, so in this case, you traverse this tree from top to down, okay, and whichever value is encountered at the leaf level, that you note down. Okay, so that is this terminal symbol. So start from here, top to down, left to right. Okay, so I start at this point, I come downwards, and at this point I encounter this A. Okay, so I'll note down this A. Again come on top, again come down, go towards the downmost point, and then you encounter B. So note down this B. Then again come on top, okay, again come down. When you reach at this point, that is when you reach at the rightmost end this side, okay, you write this symbol. Okay, so I encounter C, I note it down, come on top. Now when you reach at this point, you encounter U minus, so I'll note this U minus. Then when you reach on top, you encounter multiplication, so I note down that. Again go on top, come down, again come here, you encounter B. Again come on top, come this side, come down, you encounter C, so note it down. Come on top again, you encounter U minus. Come on top, when you reach at this point, you encounter star, that is multiplication symbol. Then you come on top, you encounter plus, and finally when you come on top, you encounter equal to. Okay, this is called as postfix notation. Okay, so how to write this postfix notation expression? You traverse the tree from top to down, left to right. Okay, so start at this point, come down till you encounter the first leaf here. When you reach at this point, that is when you come over here and you reach towards right hand side, okay, you note down that value. Again come on top, come down. When you reach at this point, you encounter this B, so note it down. Again come on top, don't note it down. When you come towards the right hand side, that time you will have to note down this star. Okay, please remember, start at this point, come down. When you reach at this point, note down this. Then again come down towards the downmost level, note down this B. Then you encounter this C, so note down. When you reach at this point, that is right hand side here, you encounter this U minus, so note it down. Again come on top, you encounter this star. Come on top again, come down, because you have some more values downwards. Okay, so note down this B. Again come on top, you encounter this C, note it down. Come on top, you encounter this U minus, then star, then plus, and then equal to. This representation of syntax tree is called as postfix notation. Okay, the next part is something called as syntax directed translation, and there is one more term called as syntax directed definition. Okay, so what is the meaning of syntax directed definition, which is represented as SDD? Okay, syntax directed definition. Normal grammar rules, say if you consider this, normal grammar rules with some actions associated with these rules. Okay, so if I write say if you consider this rule, okay, this is a valid grammar rule, there is action associated with this. Okay, so that is s dot nptr, that is the value associated with each of value associated with each of this production rules. Okay, that is called as SDD. Okay, there is one more term called as syntax directed translation. Context free grammar along with some actions and semantic rules attached to the productions. Okay, so let me give you all one simple example here. So if I write E gives E plus T and say print something, say print plus, then again I write E gives E minus T and some action, say print minus, and so on. Okay, so these are called as, that is grammar rule with some action associated with them. These are called as syntax directed definitions. What is syntax directed translation scheme? This syntax directed translation scheme is grammar rules with some semantic rules. These are semantic rules with some semantic rules. The only difference between SDD and SDT is over here when you consider this grammar symbol. Say if I consider this S, the value that is non-terminal symbols will have some attribute values. Like if you see here the semantic rule, there is one variable called as NPTR. Okay, so this is attribute associated with this symbol. Fine. So similarly over here in place of E, that is for E, there is one variable or attribute called as NPTR. Fine. So SDD, that is syntax directed definition, just consists of grammar rules and this statements, some actions. Whereas in case of SDT, you will have actions, that is the semantic rules. Along with that, this grammar symbols, that is non-terminal symbols, will have some attributes associated with them. Okay, so that is the difference between SDD and SDT. Okay, directed acyclic graph we have already seen in previous code. Okay, now the next one is three address code. Okay, next representation is three address code, wherein we can have statement of the form x is equal to y operator z, wherein each of the three address statement can contain at most three addresses. At most three addresses. Okay, so if you consider x, y, and z, in this case there are three addresses. If you consider x is equal to y, checking whether this is a valid three address statement or not. Yes, it is a valid three address statement. Why? Because there are less than three addresses. So x and y, only two addresses. Now if I consider x is equal to y plus z into q, okay, how many addresses are present now? How many variables to you should not have more than one operator here. Okay, so in this case, this statement contains x is equal to y plus z into q. There are two operators. Okay, you can have at most one operator. Okay, so x is equal to y is valid statement. If you consider x is equal to y plus z into q, this is not a valid statement. Okay, so what we do is we try to convert this statement into three address code statements. How do we do that? So in this case, what I'll do is I'll follow the rules of precedence, that is multiplication is performed first and then addition, and then finally once this value is computed, it is assigned to x. So this full statement will be transformed into three address statements as. So what we do is for evaluating for valid three address statements, in order to obtain valid three address statements, we create something called as temporary variables. So I'll create one temporary as t1 and I'll perform this operation, that is z into q. Now if you consider this statement, is it a valid three address statement? Yes. In the next thing, what I can do is I can add this y to this computation. So I'll create one more temporary, t2 is equal to y plus t1. Okay, so this part is computed, y plus t1 is computed. Finally, I can write x is equal to t2. Okay, so given any statement which is not a three address code statement, that statement can be converted to equivalent three address statements. Okay, so this is a simple arithmetic, a simple statement consisting of some arithmetic operators. Okay, we shall see some more constructs in C, like how to convert those statements into three address code statements.